All right, so moving along with the rest of this review packet. 4344 asks you to use the grid at the right to graph the equations below, then use the graph and answer 46 through 47. So we're not going to graph this precisely with a little XY chart. What I really want you to get out of this is this idea that if I look at this, f of x equals x squared, and I ask you what the vertex of this parabola would have been, that it's just the 0, 0. That's kind of our basic function. We call it the parent graph. All the others are based off of that. And then if we were to kind of sketch that in, it's just a parabola that opens upwards. Okay. So if we sketched in something like that, 0, 0 is your vertex. It has a positive 1 in front of this. So that means that it opens upwards. That's what that graph largely would look like. Then if we go to this one, think about what your vertex would be. That has a vertex of 2, negative 9. So if I plotted that point, here's 2, go down to negative 9. This also has a 1 in front of it. So basically the same parabola. It just got shifted down a little bit, and then it got shifted to the right a little bit. So this is the original. That was the F graph, and then this was the G graph. So in 43, in terms of how does G of x compare to F of x, we would just write that G of x is shifted right 2. So if you look at the vertex here, that's why the x coordinate was a 2 from 0. And instead of the y value of 0, it's the y value of 9. So it went to the right 2 and then got shifted down 9. All right, that's how we changed that graph, by just moving the vertex around. If I ask you for the x-intercepts, we did a few of those in the first half. If you watch that first video, if you've done problems 1 through 42, we had a few of these where we talked about the x-intercepts as your solutions, or what we're going to use here, they also refer to our zeros. So what we're going to do is take this function for g of x. I'm just going to recopy that right now. And I want to know, when does that equal 0? So we set those equal to 0. And then we would solve this equation. To me, the easiest way to solve this is using our square roots. So I'm going to add this 9 over. So that I get 9 equals x minus 2 squared. To get rid of that squared, this is when we do our square roots. And we know that we're going to get a positive and a negative answer for this one. So I'm going to do this over here. So I'm going to get this x minus 2 first. And then the square root of 9 is a 3, but we should get both a positive 3 and a negative 3. And then this is our two equations that we now set up. We take x minus 2, set it equal to the positive 3. We take the x minus 2, set it equal to the negative 3. Add 2 to both sides. One solution should be a 5. So that just means this graph would have crossed at 5 if I would have continued this on. If I add 2 right here, this one would have crossed at, if I can squeeze that in there, at a negative 1. So this graph would have crossed right here at the negative 1. So again, just keeping in mind, x-intercepts are the same as your solutions, which are the same as your zeros, effectively telling us to take that function value, in this case it was g of x, and let it become a 0. Do that substitution, and then solve the result once we substitute that in. This one largely the same. X squared is the basic 0, 0 graph of a parabola that opens upwards. This vertex here then is a negative 7, negative 1. So now I'm going to go left to the negative 7 and then down to this negative 1. And then it's now just going to open upwards. So what we've done is we shifted, what we do, left 7 units and 1, well, let's do down first, down 1 unit. Then I want to know, what are the x-intercepts for g of x? So again, x-intercepts are your zeros. So I'm going to take this equation here, the g of x, equals x plus 7 squared minus a 1. And instead of g of x, if it's a 0, I'm going to replace this g of x with a 0. We now have an equation that we want to solve. So I'm going to add this one over. I'm going to use the square roots to solve this. So I get 1 equals the x plus 7 squared. Then I'm going to take that square root to get just x plus 7 by itself. On the other side, I have to do the same thing and take a square root, and that's where we know we have both a positive and a negative solution, so positive and negative 1. And then from there, we set up our two different equations. I'm going to take x plus 7, set it equal to the positive 1. I'm going to take the x plus 7, set it equal to the negative 1, and we should get negative 6 and negative 8, which makes sense when I just sketched it in, pretty much where we went through. Okay, so it's those. All right, I think we already did some factoring, but when we were factoring them before, all we did is left them in factored form. Now we are solving by factoring. So we're still going to look for the numbers that multiply to be a negative 60, while at the same time adding up to be a positive 7. So that thought hasn't changed. That's what factoring means when we have this nice little trinomial here. So what are we going to get? 5 and 12. So we're going to factor this to be numbers that multiply to be a negative 60, but add up to 7 would be a positive 12 and a negative 5. Multiply those, you get the negative 60. Add them, you're going to get a 7. Now that this is an actual equation, we have an equal sign set equal to our 0. This is when we did that extra step now, and I would ask what makes this factor a 0? Well, that would be negative 12. And then I would ask what's going to make this factor equal to the 0? That would be a positive 5. So those are our two solutions. The rest are pretty similar. I'm going to factor this to be x minus 8, x minus a 5. Multiply those together, we get a positive 40. If you add negative 8 and negative 5 together, you're going to get a negative 13. So the number that makes this factor a 0 is a positive 8. The number that makes x value that makes this factor a 0 is positive 5. All right, completing the square. Did a few of these as well without having to solve them, but this is our, x squared plus 8x, and then I'm going to leave that little plus 1 behind. And then we want to make that a perfect square. So if we think about our squares, if we use our little square model if we need to, we have x squared right here. And the fact that I have a total of 8 x's means I would have 4 x's here, 4 x's here. That would have told us that I'm taking 4, multiplying it by a 4. I complete this square with a 16. So I'm going to add that 16 here. And then since I've just added this 16, it wasn't part of the original problem. I can't technically do that. So I'm going to be subtracting that 16 from that 1 that we were ignoring initially. Go ahead and solve this, or simplify that into our perfect square, which is the x plus 4, x plus 4. And I write it as x plus 4 squared. Over here, we end up with the negative 15. And then that's going to equal 0. Solve this like we did those previous couple. Well, when we go back to those graphs where I want to isolate that square term. So completing the square means I complete that square, and then I want to isolate the square. And the reason I want to isolate that square is so that I can get rid of it using the square root. So square root, the square root, we get both positive and negative 15. The square cancels out the square root. And then we get positive negative root 15. There's nothing we can do with this one. The ones that we were doing up here earlier worked out nicely because the square root of 1 is a nice 1. The previous problem, the square root of 9 is a nice 3. So we get positive negative 3. Our issue with this, not much you can do with this square root of 15. So our two equations, is you could say x plus 4 equals a positive root 15. And x plus 4 equals a negative root 15. And then just subtract the 4 from both. So x would be root 15 minus 4. And then this one, when I subtract the 4, I get a negative root 15 minus a 4. So a little uglier numbers when we don't get those nice perfect squares. All right, 50. Same process where I want to do x squared minus a 4x. And then I'm going to ignore that 3 and leave that on the back end. Then I'm going to create a perfect square out of that x squared minus a 4x. So to do that, I would have had a negative 4. I would have split those evenly, 2 in the upper right-hand corner of our box, 2 in the lower left-hand corner of our box, actually negative 2 and a negative 2. Those would have been multiplied together to create a 4 in the bottom right-hand corner when we're doing this. This would have been a 4. So I'm going to add that 4 out of nowhere. I need to subtract the 4 on the back end. This then becomes x minus 2 squared minus a 7 equaling our 0. From there, we now want to isolate that squared term. So I'm going to add that 7 over. Add 7 to both sides. Once we've done that, we do our square root. So x minus 2 is equal to both a positive and a negative root 7. The other way, we kind of split these up into 2 different equations last time. You could also just say I'm going to add 2 to both sides, and then we could actually express this as a positive negative root 7 plus 2. That would be acceptable as well, but you can also split them up and write them 2 different equations like we did up here. Either way is going to be fine. All right, then we get to a couple quadratic formulas. These we were pretty efficient at when we did them. First and foremost, real quick, let's talk about what the quadratic formula is. So negative b plus or minus b squared minus 4ac. That's all underneath the square root. And then all of that gets divided by twice a. Conditions to use this, we have to have these in the right order. So you've got to have the x squared term and then the x to the first term, and then your constant in that order, moving from left to right. And then it has to be an equation as well set equal to your 0. Once we've done that, then the first number here, 2 is an a, the number in front of x, that 1 is going to be your b, and then the c stands for your constant, the number without that variable. So that's the formula. That's what our a, b, and c are in this particular instance. Next step then is we're going to take those and plug them in. So I want the opposite of b. Well, b is this 1 right here. So it's going to be a negative 1. Then I'm going to do plus minus square root. Take your b and square it. Again, the b is a 1. Then we're always going to have this minus sign. Always going to have that 4. And then I want to multiply by a. And then I want to multiply by c. This is your a, the number in front of the squared term. So that's going to be 2. This is your c, the constant hanging out at the end. That is a negative 10. And then all of that is divided by twice a. A is that 2. All right. From there, I'm going to clean it up. Let me erase this so I can have some space. So this would now be negative 1 plus minus the square root of 1 squared, which is 1. Here's where we wanted to be careful. This is the most common spot where people are going to miss this. I'm multiplying all of these together. So I have a negative 4 and a 2. So the negative 4 and 2 make a negative 8. But then this negative 8 needs to get multiplied by that negative 10, which then should give us a positive 81. And then the denominator, a 2 times a 2 is 4. From there, we simplify underneath the radical further into an 81. I'm sorry, this would have been an 80. I'm thinking ahead a step. And then an 81, when we do the 80 plus the 1 equals 4. And then this is a nice one because the square root of 81, this is a nice perfect square that we're finding the square root of, and it just becomes a 9 over your 4. And then this should give us our 2 different answers. When I do a negative 1 plus 9 divided by 4. And the other one is when I do a negative 1, and then I have to subtract. So I'll do this minus 9 divided by 4. Then we just simplify those. This is 8 divided by 4, so that answer is going to be 2. This is a negative 10 divided by 4, so negative 10 fourths, which when I reduce should be negative 5 over 2. That's our quadratic formula. We were pretty good with those, so hopefully we remember that. Next one, same process. Formula, I want the opposite of b. b is a 5, so this is going to be a negative 5. And I'm going to do plus minus the square root of b squared. So in this case, that's a 5 squared. Minus 4 times a times c. Here is our a. Here is our c. And then all of that gets divided by twice a. Our a is, again, that leading coefficient of 4. Next step, clean up underneath the radical. So the negative 5 and that plus minus are going to stay. This 5 squared becomes 25. Same thing here, just be careful how we're multiplying all of this together. So that negative 4 times 4, that's going to give you a negative 16. And then I actually need to do this myself, 16. So that negative 4 times 4 is a negative 16. Negative 16 times 20, negative 21 is a positive 336, all divided by 8. From there, continue cleaning up underneath. That is going to give us 361 over 8. I think that's a perfect square. Let me just make sure it is what I think it is. Yeah, 19. All right, so that should give us negative 5 plus or minus a 19. Just plug this into your calculator. You'll see that it's actually a perfect square of 19, and then all over 8. And then set up your two equations. So one of them, I'll do negative 5 plus the 19 over an 8. The other one, I'm going to do that negative 5, subtract the 19, and then divide by 8. So this is 18 over 8. Not 18 over 8. Pardon me. Where am I here? What did I just do? So here we go. This is 14 over 8. And then that should reduce. 2 goes into both of these. It goes into 14 7 times, and then 8 4 times. So that's one of our answers. This one's a little nicer. Negative 5, negative 19 is a negative 24 divided by that 8. So our second solution is the negative 3. All right. So again, kind of keep in mind when we said these are our solutions, that means if we were to graph this on our calculator, it would cross the x-axis at 7 fourths and that negative 3. All right. All right, next couple, pretty straightforward. When we simplify radical expressions, it's really just us combining like terms, and it behaves similar to when we did variables. So when we look at this here, we can add constants together, the numbers that do not have the radicals attached, those square roots attached. So a 13 and a 4 is a 7. But we also have like terms of radical 3, or I'm sorry, radical 5. So I can take this 8 root 5 and this negative 6 root 5, combine those, and I end up with a positive 2 root 5. And then that's it. Cannot combine those. This is a constant, or, I guess they're both constants, but this is our number without the root 5. In order to add them, they'd have to have the same radical attached to them, and they do not. Next one, we have a 10 root 3 here. We also have a root 3 right there, so those we can combine. And you'd see there's a positive 10 and a positive 5. So when we add those, we get 15. And then that root 3. And then we also have those constants, negative 9, negative 13. Combine those to be a negative 22. 55. Initially, we can't do much with those because those aren't like terms. We can't add them and subtract them if they're not the same, like we did in 53 and 54. But this then gets into when we simplified radicals. So if you remember root 19, we always look for kind of a perfect square that goes into our number. That's also that's a factor that goes into it. So in this case, that would be the 9 and times a 2. For a 50, I would want to use 25 and 2. 25 is our perfect square. And then for that 8, I'd use 4 times 2. Simplify each of these. The square root of 9 is 3. So this is really 3 root 2. The square root of 25 is 5, and then our root 2. And then the square root of 4 here is 2 root 2. And then now what you see has happened. This isn't always going to happen, but we have a root 2, a root 2, and a root 2. So that just means we add all of these together. So the first couple, 3 plus a 5 is 8, and then take 8 and subtract that 2, should give us 6 root 2. 56. The same process for 27. Our perfect squared we'd like to use is 9, and then that times 3 gives you 27. For 48, pick the biggest one, like 4 times 12. So a root 4 and a root 12 will give you 48. But this isn't the biggest one because you're going to have to do more work to simplify 12. So to get your 48 and use that biggest perfect square, we're going to want to use 16 times 3. For 75, I think that one's pretty obvious. I think we'd all get that pretty quickly. That's a 25 and a 3. Just like before, simplify each of these. Square root of 9 is 3, and then we have that root 3. The square root of 16 is 4 root 3. The square root of this 25 is a 5 root 3. All of those end up being root 3s, root 3, root 3, so we can combine them. 3 minus this 4 should be a negative 1, and then take that negative 1, subtract that negative 5, we get a negative 6 root 3. All right. Next ones. The next handful of questions deal with the idea that we did somewhat recently. The idea that if we do the square root of a negative 1, that is defined as the number I. So whenever you see an I, that means we're dealing with a negative 1. The other thing that's going to pop up here shortly, maybe not in these next couple problems, but here before we get done with this, is that if I now square both sides, so if I square I, that means I'm also squaring the left-hand side, and the square cancels out that square root, leaving us with a negative 1. So these we want to know. Whenever you see the letter I, that's a root negative 1. Whenever you see I squared, it's a regular negative 1. So when we look at 14 or 15 or 57, the way we approach this, I would have written that 15 or 14, and the way we would have split this up, I would have said, let's take our 25 normally, with the square root of 25, and then the negative, we're going to write as a negative 1. If you think about it, if I did 25 times a negative 1, that's going to give me this negative 25, but we're just splitting it up. That now allows us to write this as this is a 5, square root of 25 is 5, and then the square root of negative 1, we said right over here, is an I. So we write this as 14 and then plus a 5I. 58, pretty much the same. I'm going to do 10 minus, and then I'm going to split the 49 in the negative 49 into a positive 49 times a negative 1. So these guys together still give us the original negative 49 underneath the radical. Now when we go to simplify this, I'm going to get 10 minus 7, and then the root negative 1 is I. That's it. All right, 59. If I want you to do this in point-slope form, A and B should be really short and sweet. This is what we've been doing recently here the most. So point-slope form is this. So something to put on your note card potentially, just to make sure we know which one it is. All I need is a slope and a point. If you notice, I gave you both of those, slope and a point, slope and a point. So letter A, I'm going to take my slope in letter A, which is a 5. That's going to go in the front position. Then I should have parentheses, and I should have x minus my x coordinate. The x coordinate of the point you were given was this 10. And then I should have a plus y. The y coordinate of that point is a -4. So we would just do -4. Same thing with letter B. The slope of letter B is this -5/3. The x coordinate in the point I gave you is this -2. So I would do x minus the -2. So this is when we see that little plus positive. And then our y coordinate at the end is that +1 right there. So we do a +1. Now, 60, largely the same. It's just our issue is to write an equation in point slope form, you're going to need to know what your slope is, and we weren't given that. So we just have to remember our slope formula. So the slope formula is the whole y2 minus, I think we've already done this on that video, the previous video. So for this problem, the y coordinate in the second point is 6 minus the y coordinate in the first point, which is a 3. In your denominator, you're going to do the x coordinate in the second point. That's the -9. And then subtract. Then I want the x coordinate in the first point, which is a 6. Simplify. The numerator is going to be a 3. Your denominator is going to be a -15. That should reduce down to be a -1/5. Point slope form then, you could pick either one of these 2 points. I am going to pick this point right here along with the slope that I just found it to be, and I'm going to write the equation. So I'm going to do y equals my slope, and then x minus the x coordinate of my point. Since I picked this point here, my x is a 6, and the y coordinate in that point is the 3. B, my slope, I'm going to do y minus y. So I'm doing 7 minus the -1. My denominator, I subtract my x's. So I'm going to do 1 minus 5. We get this little double negative that's fairly common. So you're going to get an 8 there. You're going to get a -4 here. So the slope of that line is going to be a -2. I'm going to use that slope. I'm again going to use this first point. So my equation becomes y equals -2. And then I would do x minus the x coordinate on my point is this 5 right here. And then the y coordinate is this -1. So then I just subtract 1. Those we should be pretty good at. We've been doing that now for the last few weeks with all this piecewise stuff and absolute value. So hopefully we've got a handle on that. All right, moving along. 61, 2, and 3. Again, what we just got done working on are piecewise functions. If you now notice, we have 3 different ones. We have 1, 2, 3. So we should have 1, 2, 3 different parts to our piecewise function. First one, I want to write the equation of this line right here. Again, recall this is a horizontal line, the first one. And the equation of a horizontal line is always y equals, and now just look at that line. And if I ask you what y value does that line always have, hopefully it's pretty obvious that this always, at this point, this point, this point, and this point, we always have that y value of 4. So this means y equals, and then I put my 4 right there. We then want to define the interval in which that is defined at. This horizontal line starts at the x value of 0 over here, if you look at the graph. So I'm going to start my interval at 0. And the horizontal line ends at the x value of 4. So I'm going to go 0 to 4. That's when I have that horizontal line y equals 4. All right. The next 2, though, aren't horizontal. So the next 2, we're going to rely on that point slope form that we just got done doing. So the first thing I'm going to do, I just want, if I'm going to go from this point to this point, these 2 big red points, I'm going to go down 1, 2, right 1. So I go down 2, right 1. So my slope is -2 over 1. So in my equation, I'm going to come on over here. I'm slotting in the -2 as the coefficient of those parentheses. We can use any point. I'm going to use this point right here. That point has the coordinates of 4, 4. So we come back over to our line. The x coordinate is 4. The y coordinate here is a 4. So let me erase this y. And I know that is 4. Need the interval for that one. So this line starts at 4, and then that line ends at 5. So I'm going to go from 4 to 5. Although we want to leave one of these open, so I'm going to leave that 4 open. So that just goes all x's between 4 and 5. Last but not least, this third line, I want the slope of this third line. I'm going up 1, right 1, up 1, right 1, up 1, right 1, up 1, right 1, up 1, right 1. So that slope is a 1. I'm now going to use this point right here for my point, and that has coordinates of 5, 2. So I would do x minus 5 and then plus that 2. That line starts, so this line here starts at 5. And then this line continues on until we reach this point right here, and that point has an x value of 10. So that last line starts at 5 and finishes at 10. That's our piecewise function. All right, 62, 63. The domain are x's. So what x value do we start at? What's our smallest x value? What x value do we end at? So this is now for the overall graph. So let me clean this up a little bit. Eliminate all these distractions within this graph. So if we look at this graph, it's a continuous graph. We don't have to worry about anything getting split. And we would just look, domain are your x values. Well, this starts at the x value of 0. And then this graph ends at the x value of 10. There are no breaks. So my domain is 0 to 10. You can also use these interval notation ways of writing it. So we also could say 0 less than or equal to x less than or equal to 10. Same thing. 63, range. These are the y values that we hit. So if we now look at our graph, the lowest point on this graph is right here. So that's the y value of 2. The highest point on that graph is right here. That is the y value of 7. Again, no gaps, no holes, nothing real tricky about this. My range, the lowest y value is right here. That's the y value of a -2. So I'm going to use a bracket, -2. And then I hit all the y values until I hit here, and that y value is 7. So 2 to 7. Did I say -2? It should be +2. All right, next one. Pretty much same thing. A little trickier in terms of since there's a gap here, but let's kind of do our same process. Here's my first line. Here is my second line. So there should be now just 2 parts to this piecewise function. We want to identify the slope of this first one. This one goes down 1 and then right 1, 2, down 1, right 2, down 1, right 2. So that slope is a -1/2. So I'm going to put that over there. Again, you can use any point. I'm going to use this point right here. That point has coordinates of a -2, and then its y coordinate is 4. So my line then, once I've identified that point, I will have x minus, and then I'm going to use this x coordinate, -2. So there's our double negative we know we end up getting as a positive. So x plus a 2. And then the y coordinate of that point is a 4. So x plus 2 plus 4. That one. This point starts here at the -2, and then this line continues on and on and on and on and on until we hit this point right here, which is 4. So we start at -2, we finish at 4. Second line, we need its slope. This one is up to right, or no, let me get some good points here. Anticipating a little too much. So this one up, 1, 2, 3, right, 1, 2. 1, 2, 3, up, right, 1, 2. So that slope is 3 over 2. All right, we go up 3, right 2. I'm going to use this initial point, the first point. This point here has coordinates of 5, 0. So my equation should be x minus that 5 plus that 0. And then this line here starts at the x value of 5. And then that point goes on and on and on and on and on and on until we get to this spot and finishes at 9. If you notice, this is an open dot, so that means we don't want to put this equal sign here. The open dot means it's not included, and the equal sign would mean that it is, so we want to erase that. That's our piecewise function. Range. These, again, are your y values. So the smallest y value that this graph hits, let me clean this up real quick. So the smallest y value that this graph hits, so here's this dot right here, that's the lowest point on our graph. Come on, you. All right, give me a minute. I'm gonna switch my pens. So the right range, the lowest point is right here. So we want this y value. And then if you notice, the highest this graph is going to go is up here. And then we should hit every y value in between. So this range starts at the y value of 0. Okay, here's 3, 2, 1. This would have been our 0. And then we hit all the y values until we get up to this y value of 6. But since there's this open dot here, we do go up to 6, but we don't actually ever touch 6. So the open dot meant a parentheses, and then that's our range. All right. Whew. These guys, absolute value functions. So the way we did these, we always tried to identify what is our vertex right here. That vertex is a -2, -1. And then we want to know what is this slope. This slope is up 2, right 1, up 2, right 1, up 2, right 1. If I come over here, this one is down 2, right 1, down 2, right 1, down 2, right 1. So that's a -2. Since this guy is opening upwards, we know when we go to write our absolute value function that since our slopes are 2 and -2 and we're open upwards, that we are slotting a 2 in front of our absolute value bars. If it opened downwards, this 2 would be negative. Then, since this is a -2, just like all those equations we just got done writing for lines, we would write this as x minus a -2, so x plus 2. And then since the y coordinate here is this -1, I'm going to put a minus a 1 right there. Piecewise function, we just did it. It's an absolute value function. So we know in this case, if we look up, the first slope is a -2, the second slope is a +2. And then all we got to do is basically copy what we just wrote there. X plus 2 minus a 1. We're just now using parentheses instead of absolute values. We need our intervals. So the -2 slope is over here. It's to the left of this vertex point, and that x coordinate on the vertex is a -2. So we just want all x values that are less than the -2. If you look at when do we have a slope of a +2, that's over here when we're on the right-hand side. So that's the second one, and those are all x values that are greater than that -2. All right, 67. Find our slopes. This one is up 1, right 1, up 1, right 1, up 1, right 1. So the slope on the left is positive. We do this one, down 1, right 1, down 1, right 1, down 1, right 1, down 1, right 1, down 1, right 1. So that's a -1. If I ask you to find that vertex, that is the point 0, 3. So that's all the information we would now need to know. Our absolute value function, since our slopes are 1 and -1, we know we're going to put a 1 in front of our absolute value bars. However, since this one is opening down, that means this 1 that's in front should be negative, just like it was with our parabolas. And then inside, I'm going to do x minus the x coordinate of 0. And then since my y coordinate is a 3, I'm tacking on a 3 in the back. Piecewise function. Now, if you notice, the slope of a positive 1 comes first. So I'm going to put that one first. And the slope of the negative 1 is the second one. I'm going to put that one second. I'm going to recopy this part of it and just do x minus a0 plus 3. We're still using that common point. And then you just have to understand, in this case, the slope of a positive 1 occurs to the left of that x value of 0. So this one now is x is less than or equal to the 0. And then to the right, greater than 0, that's where you get your negative slope. Those hopefully are fresh. Hopefully those are going to go reasonably well. Number 68. Since you are going to get pretty much all multiple choice on the test, here's how this would look with it being a test. It should save you a little bit of time. You don't have to do quite as much work. If we look at this here, do the same stuff that we've been doing. Identify your vertex. So this is 1, 2, 3, 4, -4, 1. Well, if we look at our options, if I ask you to write, this as an absolute value equation, you would hopefully understand we would do x minus a -4 plus a 1. So that should mean we have x plus 4 inside of our absolute value bars. All right, or I guess in this case, parentheses for our piecewise function, but definitely an x plus a4. Well, if you look at this set and this set, those are x minus a4. So there is no way that these could be our answer. So it's not B or D. We would still want to count off our slope. This is up 1, right 2. Up 1, right 2, up 1, right 2. So up 1, right 2 translates to be 1/2. If you look at the two remaining contenders here, this one is saying our slopes are 2 and -2. That clearly is not the case. Here is our 1/2 and our -1/2 would have to be A. All right, 69. Multiply those together. The 24, and then I times I is I squared. Earlier in the video, we reviewed that. So if you skipped ahead to just this problem, let me go back to where I wrote this. These guys. So this we've already dealt with in 57 and 58. The square root of a -1 is I. And then I squared is us squaring that square root. So that all we're left with is a -1. So I squared we need to know is a -1. That means I really have a 24 getting multiplied by, replace I squared with what we said it was just equivalent to, the -1. So that's how we get -24. 70, we get 30 times, and then I times I is I squared. Same thing as number 69. That really means I have 30 times a -1. So my answer is -30. All right, laws of exponents. You can see these first couple are dividing. So when we divide like terms, so that's what's happening right here. A to the 14th divided by a to the 4th. We subtract our exponents. So I would, and it's always the numerator exponent minus that denominator exponent. So I'm going to do 14 minus a 4 to get 10. And then our b's, same thought process. 5 minus 2 gives me a 3. Go to letter B problem. X to the 12th over x to the 8th. Again, when we divide like terms, we subtract these powers. So 12 minus an 8 gives us x to the fourth. 4 minus this 6 gives us y to the negative 2, which then has its own rules. So when we deal with negative exponents, which we clearly have right here, negative exponents basically imply that we want its reciprocal. We want to flip it. So what I mean by that is when we did letter A, there was nothing left over in our denominator other than a 1, and we don't really want to write that in. It's unnecessary. It's the same here. Currently, our denominator is going to be a 1. We just don't have to write it. But our issue in this one is we have this negative exponent right here. And what we talked about is what we can do to make that exponent positive is by taking the negative expression and dropping this into my denominator. That would leave us with the x to the 4 still in the numerator. But when I take this y to the negative 2 and move it into my denominator, it switches the exponent to a positive 2. And we always want, here we go, should not contain negative exponents. We always want to have positive exponents. All right. Now, letter C adds a little rule because with this now, we actually want to clean this up first. We can simplify this numerator. So I'm going to do the 4 and the 4. That's going to make a 24. And then I do x times x to the 4th. That should give us x to the 5th. And then in my denominator, still have 3x cubed. Now each set of terms we're going to divide. So first, 24 divided by 3 is an 8. And then if I have x to the 5th divided by x cubed, we just said we subtract those. That should be x squared. And then there would be nothing left over in my denominator. So we can leave that if you want, but multiple choice wise, it's just going to look like 8x squared. Last, the 4. There is nothing the 4 is getting divided by other than a 1. So we're just going to rewrite that. When we look at these x's, though, you're going to be taking the 6, subtracting a 10. 6 minus 10 is a negative 4. And then if I have y to the 8th divided by y to the 8th, that would give me y to the 0. And again, as of right now, we would just have a 1 in our denominator. But this negative exponent, come on, it's switching fast enough on me. This negative exponent right here means we want to take this whole expression and throw it into our denominator. So we are going to take this guy and we're going to put it into the denominator. So I'm going to still have the 4 on top, but now the x to the 4th is in my denominator. And then our next rule that you're going to see a bunch of here in number 72, anything to the 0 power is a 1. Basically means we don't have any y's as well. We have 0 y's, so you wouldn't have any of those in your answer. And then that's just it, 4 over that x to the 4th. The reason that is because if we just look here, isn't anything divided by itself? So if I gave you 2 divided by 2, that's a 1. If I gave you 7 divided by 7, that's a 1. So that applies to anything. Anything divided by itself is always a 1. So y to the 8th divided by a y to the 8th must be a 1. So we don't really need to show that because it just cancels itself out. So 72, these are really easy. X to the 0 is a 1. 10 to the 0 is a 1. Since this whole parentheses, everything inside of it gets raised to that 0 power, that is all a 1. 7, or D, just be careful. The 7 is not getting raised. The only thing getting raised to the 0 power is the x. So I really have 7 times, and then if I take that x to the 0 power, that's my 1, so that this one stays a 7. The 7 is not getting raised to that power. If I gave you like this one, the number is also in the parentheses. That's why that one is different than letter D. That number has been removed from the parentheses. It did not have that power of 0. All right, we're getting there. All right, 3 more. 73. So when we did all of these square roots, this is when we had a set of notes. We listed what all of our perfect squares were. So like 1 squared is 1. 2 squared was a 4. 3 squared was 9, so on and so forth. So I'll write down the first handful of these. So these are our perfect squares here. These are the numbers that we want to try and use to simplify square roots because we never want to leave a perfect square underneath our square root. All right, so for letter A, To simplify an 18, using one of these perfect squares, 9 would be our guy. So I'm going to write this as root 9 times a root 2. So that's still going to give me an 18. However, we also have some letters in here. So this is x to the 6 times y to the 5th. Square root of 9 is a 3. The square root of 2 we cannot do anything with, so he's going to stay underneath that radical. That then brings us to our variables here. And we want to be able to clean that up. So what we want to understand, we did it kind of different ways to show this. I'm going to do it down here. If I have an x to the 6th, that really means I have 6 x's. And since this is a square root, there's an implied to have a 2 there. It's an index number of 2, so that's why it's a square root. I'm looking for sets of 2. So here's one set of 2. Here's one set of 2. Here's one set of 2. I have 3 sets of 2s. So I can actually pull out this guy, and that guy. I have 3 sets of x's, so I'm going to write that as x cubed. I would have no x's remaining. We also have these y's. So I have 1, 2, 3, 4, 5 y's. Again, a square root implies I need 2 in order to pull them out. So here's one set of 2's, or one set of y's. Here's another set of y's. So I have 2 complete sets of y's. So I'm going to come back to this problem. I'm going to go y to the 2nd power. But if we look, we still have this extra y that did not have a partner, did not have a square, another y to make a complete set of 2. So because of that, he could not get taken out. He just stays underneath the radical. All right. Now, what we eventually graduated to that at the time, I think people understood, if this is a square root here, all we really need to do to figure this out is if I took 6 and divided it by 2, notice how we get this 3. So the x had 6 of them, divide by 2, we're going to get a 3. If I took 5, divide that by that index number of 2, 2 goes into 5 2 times, but that would only get us 4 of them. So we'd still have that extra y hanging out in the front. All right. Writing them out like this, nice visual. Takes a little bit of time, maybe not the most efficient, but if that helps you kind of see what's going on and how we need sets of 2, then by all means, go ahead and do it. All right. All right, letter B, 8, I'm going to use 4 and 2. And then I'd still have x cubed and y to the 10th. So 4 kind of looks like a 9. But that's the perfect square from our list over here, this list. That goes into 8. And now we clean it up. So the square root of 4 is a 2. Root 2. Cannot do anything with that. So he's going to have to stay underneath the radical. If I want a square root, I want sets of 2. So if I only have 3 x's here, try that one more time, and I need a set of 2, I can only get one complete set of x's to pull out, and I'd still have the third one remaining. So there is going to be an x that stays inside. When we go to this one, if I have 10 people and I'm trying to split them up into pairs, out of 10 people, that means I should have perfectly 5 sets of pairs. So I have y to the 5th. There would be no y's remaining. See, now I just put a number in front of it. Doesn't change anything. 24, the perfect square you want to use is 4. So that would be 4 and a 6. And then we have our x to the 11th, y to the 5th. So the 10 I'm going to drop. I'm going to multiply that by the square root of 4, which is a 2. Leave the root 6. And then, yeah, I probably could have shortened this up a little bit. Let me just rewrite the variables in here too. All right, so this gives us 20, the 10 and the 2. We still have a 6 underneath. And then now 2 will go into 11 5 complete times, but I'd still have 1 x remaining. 2 will go into 5 2 complete times. and there's still a y remaining. So then this should be our answer. All right, I'm going to erase this so I can create a little space for this one. So the last one of these, the D, I'm going to have that 2, and then I'm going to have root 4, root 10 to get the 40. And then the variables I'll just leave for right now, a to the 6th and b to the 9th. First one, the 2, stays the same. Square root of 4 is 2, so this is really a 2 times a 2. Root 10, can't do anything with it. Doesn't simplify any further, so I'm going to leave that underneath. We go to our variables. It's a square root, so I want perfect squares. I want sets of 2. Well, out of 6 people, I can get 3 complete sets, so I'm going to pull out a cubed. If I have 9 people and I'm trying to create pairs of 2, I can get 4 of those, but I would still have the 9th be left over. Go ahead and multiply these together. So the next step, I'm not going to rewrite it all. The 2 times the 2 just created a 4. And then this should be our final answer. All right. All right, last one's cube roots. So these now, if I were to make our perfect cubes, that means 1 cubed is 1. 2 cubed is 8, so 8 is a perfect cube. 3 cubed, 27, that is a perfect cube. That's about as big as I took you, because these get big really quickly. So when we now look at this, the reason we're concerned about cube roots now, all of these little index numbers, well, this should be a 3 right here. I'm going to change that to 3. Those should all be perfect cubes. So now I only want to be using these to split this up. So if I look at a 16, the number that works is this 8 right there. So I'm going to write this as a cube root of 8. And then that multiplied by 2 would give me that 16. And then I'm still going to leave the x to the 6th and y to the 7th like I did before, but we got to keep in mind this is a cubed root. When we see this cube root of 8, that's just asking what we cubed to get 8. So if we come over here, what we cubed to get 8 is a 2. So the cube root of 8 is a 2, and we can't do anything with the cube root of 2, so he's going to have to stay underneath the radical. Now I have 6 x's, but now we want sets of 3. So if I have 6 people, and I tell you to get into groups of 3, we should be able to get 2 complete groups of that. So I'm going to pull out an x to the 2. If we have 7 people, and I tell you to get into groups of 3, I can get 2 complete sets still, but there's going to be 1 person remaining, so that 1y needs to stay underneath. All right, B, same thing, 24. We want to pick from these numbers over here. The only one that would be usable is the 8 again. So I'm going to write this as a cube root of 8 times a cube root of 3. That'll give me the 24. And then I'd still have a cubed root of x to the 12th, y to the 10th. Just like before when I said this cube root of 8 is a 2, same thing should happen here. So this cube root of 8, asking us what we cubed to get an 8, that's 2. But then the cube root of 3, that guy needs to stay underneath the radical. Then we go to our x's here. So I have 12 people. I tell you to get into groups of 3. We would get 4 of those with nobody left over. It'd work out perfectly. However, if I have 10 people, this is a 10, and I tell you to get into groups of 3, we could get 3 complete groups. So I have y to the 3rd, but that would only take care of 9 of these 10. So the 10th person would have to stay inside. C, 54 now. We can finally use a different perfect cube, and that's going to be this 27 here. Cube root of 27 multiplied by the cube root of 2. That will give you the 54, and then we'll do a separate one for our variables. Cube root of 27 asks what did we cube to get a 27? You can see there that's a 3, but cube root of 2 is going to stay. We have 3 people. I ask you to get into groups of 3, we can only create one group. So that X creates one set of X's. If I have 13 people and we're asked to group into the groups of 3, out of 13 people, groups of 3, we would get 4 complete groups. That would account for 12. So the 13th person would be left out. He has to stay underneath. Last but not least, 32. 8 is the number that goes into 32. So I'm going to do cube root of 8, cube root of 4, and then our variables. Cube root of 8 again is 2. Cube root of 4, we're out of luck. Can't do anything with him. Of our 5 X's, if I need sets of 3, so I want you 5 people get into groups of 3, I could only get really one group of 3. So I'm only going to pull out an X to the first. And that would now leave, of the 5 that I had, 3 of them got taken out. There would still be 2 X's remaining. Similar thing happens with our Y's. There's 8 Y's. I need a set of 3. I want sets of 3. So if I have 8 people, I tell you to get into groups of 3. We would get 2 complete groups, but that would only account for 6 of the 8 people. So there would still be 2 people, 2 Y's that have to stay in. All right, last but not least, these should be pretty familiar to us at this point. This is what our very last quiz and test covered. Our goal with all of these is to get this absolute value bar isolated. In this case, that's already taken care of for you. Once that is the case, we know as long as this equals a positive 12 or a negative 12, then when we do the absolute value, we get a positive 12. We'll make it equal the right-hand side of 12. So we set up our 2 equations and then solve those. So I add 10 to both sides in this one. Next one, divide by 2. One answer is 11. Same exact steps over here. Add 10 to both sides. We get 2x equals a negative 2 for the second one. Divide both sides by 2, and the second answer is negative 1. Now, letter A, we already had this thing isolated. We didn't really have to do any work to do that, to get that isolated. When we now go to B, if you notice, we got some other things going on over here with this, what I'm highlighting, that we want to get by itself. So we want to get that absolute value of x minus 10 all by itself. We're going to do that by first subtracting that 2 over. All right, so here's our equal sign. It cancels that out from here, so we no longer have the 2 to worry about. That means we have to subtract 2 from the other side, leaving us with 48. But if you look at what we're trying to isolate, we still don't have this by itself because of that 3. So to get rid of that 3, since this is a product, we undo products through division. So I'm going to divide by 3 to both sides. These will cancel. And that now equals 16. So at this next step, if you now notice, we finally have our absolute value bars all by themselves. So it is now at this step that we go ahead and know that if I can get this to equal positive 16 or negative 16, when I take their absolute values, it'll equal 16. That's why we set up our 2 different equations. One set equal to positive 16, and then one of them set equal to a negative 16. Add 10 to both sides, so it'll cancel out here. The x is now isolated, leaving us equal to 26 for the left side. Add 10 to the second equation. 10s will cancel. X is now isolated, and that leaves us equal to a negative 6 on the right-hand side. All right. C, we need to divide by 2. That now isolates our x minus a 9, set equal to that 5. Set up your 2 equations. X minus 9 equals both a positive 5, and x minus 9 needs to be set equal to a negative 5. Add 9 to both sides. Cancels. The first one should give you 14. When we add 9 to this one, these will cancel. This negative 5 plus 9 is a positive 4. Those are your 2 answers for letter C. And then finally, last but not least, letter D, we want to isolate our absolute value bars. So we need to divide by this -2. Those will cancel. I now have the absolute value of x minus 9 equals a -9. This is the one you need to be careful of because this is now us. We have this hold on a minute. We have this absolute value expression here set equal to a negative number. And what I've asked you when we've done these is we need to recognize at this step that when we take the absolute value of anything, so no matter what I plug in to this x value here, I'm ultimately going to be taking the x value. And when we do the absolute value of whatever this produces is going to pretty much always be positive. The only time it wouldn't is if it's a 0. So there is no way that this positive number could ever equal a -9. So when we recognize that, this is our no solution. That is a wrap. If you guys have any questions, you're more than welcome to get in a little bit early on that day that you're taking your final. But hopefully this will help a little bit. You can go through and find any problems, and then hopefully the explanations will clear up anything that you weren't certain about. So we'll see you guys shortly. Hope you're enjoying your weekend.